In the previous video, we took a look at the triode and we actually ended up making a simple inverter circuit with it. And we got some pretty interesting results out of it. I mean, we were able to turn an LED on and off, and we were able to actually dim that LED really well. But at the end of it, we kind of ran into an issue. When I removed some of the voltage drop resistors that I had, we noticed that the LED didn't turn all the way off. And when we compared the brightness of the LED when it was on to that of the transistor, we noticed that it wasn't quite as bright. So there's something else going on kind of behind the scenes there that I'm not really sure about. So what I want to do today is I want to maybe take some measurements and look at some data sheets and see if we can figure out exactly what's going on inside the tube that's causing this to happen. And then maybe we can build a circuit that's a little more accurate and how the tube is actually supposed to be used. So let's jump over to the bench and pull out the multimeter and start taking some measurements and see what we come up with. Okay, so here we have my breadboard set up, and you can see that it's kind of split into two sections. We'll ignore this back half for now, and we'll just focus on the front half here. And you can see that we have both a triode and our little 2N222 transistor set up. And so the triode is set up pretty much exactly like before. I'll just draw it out real quick right up here. So this is pretty much essentially how it's drawn out. Each one of these resistors is listed like that. So we have a 10K resistor coming into the plate, we have a 10K resistor coming into the grid, and then the grid's pulled to ground with a 100K resistor right there. And then our output comes off of it right here. Okay, and then coming into our input here is going to be what our little black button is right there. And you can see it comes off of the 6-volt rail. So we have this little buck regulator here that's creating 6 volts out of the 24 volts from our power supply to drop it down to a voltage that the heater in the vacuum tube can use. And right now everything's off, so we'll go ahead and turn the power supply on. All right, it's running at 24 volts, and we'll give the vacuum tube a second to warm up. All right, now what I'm really curious about, what I really want to know is what the output voltage is doing for both the transistor and the vacuum tube. So the transistor is set up pretty much identical to the vacuum tube. The only difference is that the transistor doesn't have this 100,000 ohm pull down resistor on the input there. But other than that, it's pretty identical. And our 6 volts that comes in actually goes through a 10,000 ohm resistor first, and then it comes down and splits and goes to both the transistor and the vacuum tube. So we'll look at the output for both the transistor and the vacuum tube. And we'll do it when the button is pressed and when the button is released. All right, but I want to do it without these LEDs in place because they can kind of create a change on our output here that maybe we don't really want to see. But before we do, let's go ahead and just push the button and see what the LEDs do. All right, well look at that. The blue LED for the transistor turned off completely. But the green LED for the vacuum tube only dims. So we know there's something fundamentally different going on right there immediately. So we'll go ahead and pull the little blue LED out here. And I'll just use my probe here to measure our output voltage. All right, you can see that's 23.7 volts. That's pretty good. That's pretty much source voltage. That's exactly what we were hoping to see. Now if I push the button, wow, look at that. You can see it drops all the way down to 90 millivolts, which is pretty much nothing. So we'll just go ahead and write that as 0.09 volts. That's way down there. That's really good, actually. All right, well, let's do the same for the tube here. Let's go ahead and pull the LED out there. And we'll just measure the output here. Whoa, you can see that's a huge difference right off the bat. I mean, that's only 14.5 volts. So we'll write that down here. That's 14.5. All right, now let's push the button and see what happens. Oh, hey, we're getting a higher voltage out of it that time. I think my voltmeter's not all that great. So we'll change our number down there to 16 volts. Then I push the volt, you can see it drops all the way down to 4.9 volts. Oh, now we're at 14.6 volts. So things are changing kind of interestingly in here. But what we're seeing is that we're getting a consistent 4.9 volts when I push the button. All right, so we'll leave that as 14.5, but then we go down to 4.9 volts. So we have something very interesting going on here. You can see that the transistor goes pretty much from 0 volts to source voltage, which is 24 volts. That's a really nice swing, and that makes doing binary things very easy. But you can see that the tube has not that at all. We've got essentially 5 volts to 15 volts. Now we do get a 10 volt swing out of it, which is pretty good. But we're not seeing source voltage here. And if we're not seeing source voltage here, that means that there's some electron flow going through the tube. All right, so if we draw our vacuum tube out here, the electrons that get thrown off here are trying to seek their way up to the plate. But if this grid has a negative charge to it, you know, like-minded particles repel each other. So those electrons shouldn't get here. So they should be stopped there. But some electrons have to be getting through because we're seeing only 15 volts here. So, well, we're pulling this to ground. Why isn't it blocking the electrons? Well, in order to understand that, we need to take a look at the data sheet. Well, on the first page of the datasheet, we're not really going to get our answer. So we'll move a little further down the datasheet towards the graphs in the back. Now, there's a lot of different charts going on here, but the one that I'm really interested in is this chart right here. And this kind of shows the plate characteristics here. Now, you notice this is for a Philips ECC88 tube. But the ECC88 and the 6DJ8 tube that I'm using are equivalent tubes, so this should be pretty equivalent. Now there's something right off the bat by looking at this. Even if we don't know how to read a tube chart, maybe we're doing something wrong, because this VG here is the voltage of the grid. And you can see, well, the highest voltage that's listed is 0 volts, and it goes down from there. We have -1 volt, -2 volt, -3 volts, -4 volts, -5 volts, -6 volts, 7 volts, 8 volts, 9 volts, all the way down to 10 volts. And then along the bottom here, we have our plate voltage. And you can see that the plate voltage for this graph goes all the way up to 300 volts. So we know right off the bat that we're misusing the tube by using it at 24 volts. But even so, this doesn't list any grid voltages above 0. And with our current setup, well, we don't have any negative voltage going to the grid. We only have either 0 or positive voltage as our input into the grid. And, well, that creates a bit of an issue. We have two problems that stem from this. The first is that, one, the tube was never really designed for that. But the other problem is that we end up with electrons going into two places if we put the grid at a positive voltage. All right, so if we draw our tube out here, I'll draw it nice and big. So this is our cathode, which we are hooking up to ground, and we've got 24 volts up here, essentially. So these electrons definitely want to get to that plate. Now, if we take the grid here and we give it a positive voltage, say, whatever, you know, say 2 volts. Well, that's a positive voltage. That's opposites attract. So some of these electrons are going to find their way into the grid and flow out of the grid as well. Well, this is now an interesting situation. We have essentially two circuits going on, and the electrons are coming from one place, but they're going to two different places. And that makes it very hard to track what's going where, but also, more importantly, the grid was never designed to have electrons flowing into it. And when I draw these, I draw the little dots, but the electrons move at insane speeds. That's why there has to be a vacuum inside the tube. And if those electrons are running into the grid at those really high speeds, it can start to heat the grid up. And the grid was never designed for this. So the lifespan of the grid can start to plummet, it can start to go down. So it's never good to put a positive voltage onto the grid that they can start to pull voltage out of it. So we need a negative voltage. But how much negative voltage do we need? Well, we'll just take a quick look at our chart here, and remember we have a plate voltage of 24 volts. So that's pretty much just this bottom corner here. Now, 24 volts intersects with our -1 volt line right here. So we're aiming for essentially 0 plate current. That means that there's no electrons flowing through it. And so in order to get 0 plate current, well, we have to essentially hit -1 volts. And so if we put a -1 volt charge on our grid, that should theoretically pull the tube into cutoff, and we should see our output change from 15 volts all the way up to source voltage, which is 24 volt. But these tubes are used and they're old, and the more that they get used, the more hours that get on them, this accuracy may change a bit. Also, 24 volts is an extremely low plate current, and the tube was never really meant to operate at this low plate current. So this may actually not be that accurate of a chart for us. So we should probably overshoot a little bit. Let's maybe aim for, say, a -2 volts. But how can we ensure that we get -2 volts onto the grid, and we can come, maybe a little bit past 0 volts or up to 0 volts whenever we have our input going on? And we can't just replace our 100,000 ohm resistor with negative voltage. That would make things much harder to calculate and figure out. And we're hitting a point where we need to start planning. But it seems like quite a daunting task ahead of us. So what do we do from here? How do we figure out what the circuit needs to be? And the simple answer is we cheat. We look at what other people did back in the day. And IBM has these fantastic customer engineering manuals where they go through all of the different type of logic circuits that they built out of vacuum tubes and how they built them. So let's take a look at what IBM did, and maybe we can get some ideas from them. So this is the Customer Engineering Manual of Instruction for the IBM 604, which was called an electronic calculating punch. And if we scroll down a little bit, you can see it was quite a big machine, but it was a vacuum tube machine, and there's a ton of fantastic information in here. Now this is several hundred pages of wonderful information, and if you have the chance, I would highly recommend reading through it. I'll put a link below to where I found this. But if we scroll down, we can start to see they start talking about vacuum tubes, and they start talking about how they were used in their system. And what I'm really interested in is they show this practical inverter circuit here. Now they have it split between a driving stage and an inverter stage, and I'm mostly interested in the inverter stage and the level of input that's coming in. Now the voltages they're dealing with are much, much higher than we're dealing with. You can see that they're using a plate voltage of 150 volts, so plus 150 through a 20,000 ohm resistor. And then they have a collection of resistors with what we call a negative bias. So you can see that instead of having the 100,000 ohm resistor pulling the grid to ground, they actually have a 470,000 ohm resistor pulling it to -100 volts. And then they have a 390,000 ohm resistor and a 47,000 ohm resistor to create a kind of an interesting collection of resistors here. And then the input coming into this is going to swing between plus 50 and plus 140 volts, which is really interesting because if we look at what the output is, it's plus 50 to plus 150 volts. So this is kind of built up to have the output of another inverter stage feed into the input of this inverter stage. This is fantastic. Let's just copy this. But the voltages are really high. I don't want to play with 150 volts. So what I really need to figure out is what is the voltage at the grid doing? So we could do the math but I found it much easier to actually just simulate the circuit in a program called Tina TI Spice. So you can see that I've set it up with the same resistor values as they did, and the B plus voltage is the 150 volt battery that's up here, and then our input is 140 volt and 50 volt here. And I just got a little switch to switch between the two. And then we have one battery hooked up backwards for our negative 100 volt bias. And so I was really curious what the voltage was doing in the middle of all these resistors, what the voltage was exactly at the grid, and then what our output voltage was. And one of the great things about this is that I can simulate it with just a nice little digital multimeter here. So we've got HV1 set up first. So that's our voltage at this kind of center point in between all three resistors. And when it's low, you can see we have negative 18 volts. And when it's high, you can see we go up to 6 volts. So that's our swing. They've got a strong negative voltage when we're at logic low and a positive voltage when we're at logic high. But remember, we didn't want a whole lot of positive voltage on the grid here. So I wonder what this 47,000 ohm resistor does. Well, let's take a look at HV2, which is measuring directly at the grid. Oh, and you can see, look at that. The voltage directly on the grid is showing 537 millivolts at logic high and negative 18 volts at logic low. So that's quite a large logic low voltage, but remember, they have a much higher plate voltage than we have. So going overkill on the negative voltage there ensures that you get proper cutoff here with a larger plate voltage. So let's take a look at our output, see what it's doing. Well, our output is 150 volts, and we swing down to 18 volts. Well, if we look at this, they said that was a plus 50 volt. So maybe our simulation isn't perfect, and that's totally understandable. Most of these simulations weren't meant to use vacuum tubes. This was a custom model that I downloaded. So it's not perfect, but it gives us a really close idea. And so I think that if we look at the grid voltage of a strongly negative voltage and then minutely positive, a half volt or less on the grid, well, that'll get us pretty close to what IBM's doing. But we need to adjust all these resistor values to work with our lower voltages. And so that's what I've done over here. So on the left, we have our high voltage version, the IBM version, and on the right, we've got our low voltage version. This is our version. And I happen to have a lot of 100,000 ohm resistors and 10,000 ohm resistors floating around, so I figured I'd just give those a shot first. And who knows, maybe I got lucky. So if we open up our digital multimeter here, and we take a look at low voltage 1, which is in the center of our three resistors here, we can see that we've got minus 2.5 or 2.8 volts. And you can see our negative bias voltage is set up as negative 12 volts. So exactly half of our positive voltage, but in the negative direction. So that's good. Let's look at what's happening on the actual grid itself. Well, you can see it's still showing minus 2.8 volts there. But there we go. If we go back up to positive, we only got 480 millivolts. So that's actually a really good swing. We're going slightly positive, so we ensure that there's good electron flow through the tube, and we're going heavily negative to ensure that the tube goes into proper cutoff. So let's look at our output. We can see that when we're at this point, we're fully cut off. We're at 24 volts source voltage. That's fantastic. That's what we're aiming for. But when we have 24 volts feeding into the input, well, we only drop down to about 6.29 volts. And that's because we don't have additional electrons traveling out the grid. That's a good thing, but it means that our logic low is a bit higher. But you can see IBM didn't have a problem with having a logic low of 50 volts. So we can just design our logic low around 6.5 volts. So this is pretty good, actually. I have a bunch of these 100,000 ohm resistors and a bunch of these 10,000 ohm resistors, and this doesn't look all that much more difficult to set up than what we've already got. The only question is, what do we do with this negative 12 volts? How do we get negative 12 volts? Well, the easiest solution to get that negative 12 volts is to just use another power supply. And I happen to have a wall wart here with one of these neat little connections on the end that allow me to hook some additional wires on it. And this is a 12 volt wall wart. And to get the negative volts out of it, we'll take the positive of it and we'll actually hook that into the ground of our other power supply. And then we'll take the negative of it and we'll hook that up to this little orange wire over here. Now this little orange wire is going to our other vacuum tube setup here. I've gone ahead and turned the breadboard around just to make things easier. And this other tube setup is exactly like what we had simulated in our SPICE program earlier. And so with our multimeter, we should be able to see that negative 12 volts. If I check right here, there we go. You can see negative 11.6 volts. Now, instead of having a push button, I've got this little toggle switch, and that's just to do a 24 volt or a 6 volt input. Because if you remember on our simulation, well, logic low was 6 volts and logic high was 24 volts. So right now I've got the switch set to logic low. So you can see we've got 6.1 volts coming in there. And if we've got our resistor combination here, but if we skip all that and we look directly at the grid, you can see we've got negative 4 volts there. So that's actually a little bit higher than what our simulation was showing. But again, that's not a bad thing. We're ensuring that the grid is fully in cutoff. And negative 4 volts is actually right dead square in the middle of what our chart was showing for grid voltage. So we're not actually damaging anything that way. Now, if I flip the switch, you can see our LED gets a lot dimmer, but it doesn't go out completely. And that's understandable because remember our logic low was 6 volts. So we should be seeing 6 volts on the output. And when I flip back over here, we should be seeing 24 volts on the output. So I'll go ahead and remove this LED and we'll measure the output directly. Look at that, 23.6768 volts. Well, that's B+, that's our voltage source. That's awesome. We're getting a proper full output out of it. Now, if I flip that switch, we should see something like 6 volts, hopefully. So let's see here. Look at that, 6.5 volts. All right, that's awesome. So what we've done is we've created a 24 volt version of an IBM practical inverter circuit. That's amazing. Look at that. Logic high, logic low. And it's really consistent. It's super consistent. I'm super happy about that. I know it seems a little hilarious to get excited about some flashing numbers on a multimeter, but this is epic. I'm really happy about that because, well, that means that we have a logic circuit. And that also means that we now fully understand how the triode is working with the voltages that we're giving it. And once we understand that, we can start to do some really neat things. We can start making inverters, we can start making NORs or ANDs, and then we can start stacking them on each other and make some really complicated stuff. That's awesome. I'm really excited about that. There's a lot of interesting things we can do in the future. But before we start building things with the triode, there are other vacuum tubes out there than just the triode and the diode. There's the heptode and the pentode and the pentagrid converters and things like that. And well, the pentode's probably the most common next to the triode. So I think next time we'll take a look at the pentode and we'll see maybe what its differences are to the triode and see why it's called a pentode and what fundamentally about it is different. And maybe we'll also take a look at the data sheet and kind of compare the curves on that. Before I let you guys go completely, I just wanted to say that while editing this video, I found that there were just a ton of things that I didn't get to cover or that I glossed over or maybe oversimplified a little too much. And I would be remiss if I didn't go into those in a little more detail. So before we move on to pentodes, I think we'll make a part 2.5 of triodes and take a look at some of the things that I didn't cover in this video, like a comparison against transistors by looking at the charts in the back of the datasheet. Or, I said that we needed to have a negative voltage on the grid. And while that's certainly true for this tube, it's not true for all tubes. And depending on how you want to use the tube, you can tackle that problem in different ways with, negative grid leak and stuff like that. So there's a lot of topics to cover and a lot of things to do, and this is a huge rabbit hole, so I'll try to keep it concise, but there is some more that I would really like to cover, so we'll go into that next time, I think, and then after that we'll move on to pentodes.